Section 1.3, Displacement in two dimensions. Vector quantities, such as displacement and velocity, are described in terms of both magnitude and direction. In diagrams and figures, an arrow represents a vector quantity. The arrow's length indicates the magnitude of a vector, for example, how fast the car is moving. And the direction of the arrow indicates the direction of the vector relative to a chosen coordinate system, for example, which way the car is moving. In most cases, we use reference coordinates that are perpendicular to each other, such as x and y, or north and east, and then describe the vector in two dimensions with respect to this coordinate system. Here we have a vector illustrated in red. Its magnitude is 15 meters, and it is pointing 35 degrees north of the west line. The way we represent that vector is by writing its magnitude, 15 meters, and its direction, 35 degrees north of west. Now, there is another way to indicate this direction. Instead of saying 35 degrees north of west, we can write how many degrees west of north it is. To find out how many degrees west of north, we would subtract 35 from 90, because we know that this is a 90-degree angle. An alternative way to write 15 meters 35 degrees north of west would then be 15 meters (55 degrees west of north). In sample problem number 1, we're going to complete vector addition by drawing a scale diagram. Let's look at this example. Suppose you walk to a friend's house, taking a shortcut across an open field. Your first displacement is 140 meters, 35 degrees north of east, across the field, and then you walk 200 meters east along the sidewalk. Determine your total displacement using a scale diagram. When using a scale diagram, you need to first establish your coordinate system, north, east, south, and west, and then come up with a scale that allows you to draw all of the vectors efficiently on the size of paper that you have. In order to do so, my scale will be 1 centimeter equals 100 meters. So let's start by drawing our first vector, 140 meters, 35 degrees north of east. And I'm going to decide where I want to start my vector drawing. So I'm going to draw a little dashed line. And from this dashed line, I am going to set up the base of my ruler, and I'm going to angle it to 35 degrees north of east. Once I've positioned the direction correctly, then I can draw the vector using the scale. A vector of 140 meters would then be 1.4 centimeters on this page. This is 140 meters, and this is 35 degrees north of the east line. To this vector, I will add the second vector, which is 200 meters east. And when we add them, we will add them tail to tip. So I'm going to line up the tail of this vector to the tip of the previous vector, and I'm going to draw a line that is 2 centimeters long. Just going to rearrange this so it doesn't angle down. Once you've drawn your second vector and you've added it tail to tip, you can find your answer by joining the tail of the first vector to the tip of the last vector. This would be your answer. This red line represents your total displacement. And with your ruler, you can measure this line and you determine from your ruler that it's 3.2 centimeters long. Converting 3.2 centimeters using your scale, 1 centimeter to 100 meters, we know that our total displacement is 320 meters. And to find the direction, we need to find the angle north of the east line. An alternative would be to find the angle east of the north line. I'm going to find this one using my protractor, line it up, and I end up with 14 degrees. So the direction of this is 14 degrees north of east. Now, alternatively, we can use the cosine and sine law to answer the exact same question. So here we have the same question set up. When using trigonometry and formulas such as the cosine law and the sine law, it's not necessary to draw them to scale. You should have them drawn roughly to scale, but they don't have to be perfect. So I've drawn my first vector, 140 meters, and it's 35 degrees north of the east line. To this vector, I've added the second line, which is 200 meters east. And I've added them tail to tip. So we're going to use trigonometry to find the answer. Our answer is the line that joins the tail of the first to the tip of the last. So let's start seeing what we can fill in using trigonometry. So I'm going to sketch some of these lines in so that you can see them. I know that this angle is 35 degrees. That makes this angle 55 degrees. And if we use the transverse parallel line theorem and we extend this line, since vector 1 bisects these two parallel lines, then I know that this angle and this angle will be equal. So I can write down that this top angle is also 35 degrees. Now, since this forms a straight line, this angle's 35, this angle can be determined if you do 180 degrees, a straight line, minus 35 degrees. So we know this angle is 145 degrees. I'm going to label this as angle C and this as side C. We have side B, and that would make this angle inside angle B. I'm going to use the sine law. Actually, first I'm going to use the cosine law to find the magnitude of our total displacement, this line C. So I know that C squared equals A squared plus B squared minus 2AB cos C. The magnitude of A is 140. The magnitude of B is 200. So we have 140 squared plus 200 squared minus 2 times 140 times 200 times the cos of angle C, which is 145 degrees. In order to find C and not C squared, we need to find the square root of all of this. If we punch this into our calculator, we determine that the magnitude of side C is 320 meters. So this side is 320 meters. Now, I know angle C and side C. I need to find the direction that this is pointing. In order to find the direction that this is pointing, I would need to know what this interior angle size is. I know that this is 35, and I know that this is 55, but I need to find out what this angle here is, angle B. I'm going to use the sine law, which tells me that sine B over side B equals sine C over side C. So I can find the angle B, it's equal to the inverse sine of side C times sine C over side C. We can find this angle by subbing and solving. Where B is 200 times the sine of 145 divided by 320. If we punch this into our calculator, we end up with an angle of 21 degrees. So I know this interior angle is 21 degrees. So if this angle is 55 and this angle is 21, what's the remaining angle that makes up this entire 90-degree corner? In order to find the angle which determines the direction of our vector, which we'll call theta, we know theta is equal to 90 degrees minus 55 degrees minus 21 degrees. If we punch that into our calculator, 90 minus 55 minus 21 is 14 degrees. So we can state the magnitude and direction of our total displacement. Therefore, our total displacement using the sine and cosine law is 320 meters, 14 degrees north of east. We determined this angle, this angle and magnitude of our total displacement, just as we did up above, using a scale diagram. In this course, we're going to ask you to solve questions like this, and you can decide which method you prefer. Maybe you prefer to draw them, like we did in sample problem number 1, or maybe you prefer trigonometry. I want to talk about the concept of component vectors. And we'll start with an example. A polar bear walks towards Churchill, Manitoba. The polar bear's displacement is 15 kilometers, 60 degrees east of south. Determine the components of this displacement. So I'm going to set up rough reference coordinates from which I'm going to measure and draw a rough sketch of this displacement. And I need to draw this vector such that it is 60 degrees east of the south line. So we can draw a directed line segment whose magnitude is 15.0 kilometers, 60 degrees east of south. This is our vector, but we can express this vector in terms of x and y components. I can break this up into two directed line segments, one here, which is the y component, and one here, which is the x component. If you add the y component and the x component, it is equal to 15 kilometers, 60 degrees east of south. In order to find the y component of this displacement, which we will call delta dy, we can see that delta dy, we have the adjacent line, the hypotenuse line, and the angle 60 degrees. Using SOHCAHTOA, we know that adjacent and hypotenuse with respect to the angle is, adjacent hypotenuse is cosine. So I can write delta dy over the hypotenuse is equal to the cos of 60 degrees. If I want to find delta dy, I can isolate this and say delta dy is equal to 15 kilometers cos 60 degrees. If we punch this into our calculator, we end up to three significant digits, 7.50 kilometers, and this is pointing directly south. Let's do the same and determine the x component of our displacement. We know that the x component is the opposite with respect to the angle and the hypotenuse. Opposite hypotenuse is the sine ratio. So we can compute this. Delta dx, the opposite, over the hypotenuse, 15 kilometers, is equal to the sine of 60 degrees. If I rearrange this, delta dx is equal to 15 kilometers times the sine of 60 degrees. If we punch this into our calculator, we'll get to 3 significant digits, 13.0 kilometers, and the direction this x component is pointing is east. Now, breaking up a vector into x and y components is actually a very valuable tool, and we can use it to add vectors in 2 dimensions algebraically. So let's try an example in which we use x and y components to find the total displacement of 2 non-collinear vectors in 2-dimensional space. This is sample problem number 4. In sample problem number 4, we have an airplane that flies 250 kilometers, 25 degrees north of east, and then flies 280 kilometers, 13 degrees west of the south line. What we need to find is the total displacement. In doing so, the very first thing we need to do is break each vector up into its x and y components. So I'm going to start off with my x components. I'm going to call this delta d x1 because this is vector 1. And then this would be my y component, delta d y1. I'll do the same. This is my y component for vector 2. And this is my x component for vector 2. I know that the y component is the opposite with respect to the angle and hypotenuse. Opposite hypotenuse is sine. So I can determine the magnitude of the y component of this vector, and it is 250. Let me keep it in the red color, 250. Opposite is sine of 25 degrees. If I punch that into my calculator, I end up with 110 kilometers north. If I look at the x component, it's the adjacent with respect to the angle and the hypotenuse. Adjacent hypotenuse is the cosine ratio. So I end up with 250 cos 25 degrees. Now, I want you to look. When we found the y component, it was 250 sine 25. And when we find the x component, it's 250 cos 25. If one of them is sine, the other one will be cos. Now, it's not always that the y component is sine. Sometimes it could be cos. But in this case, if it's sine, then this must be cos. Let's simplify. 250 cos 25 is 230 kilometers east. Let's break up vector 2 into x and y components. We'll start with the y component. The y component, we have adjacent with respect to the angle and hypotenuse. Adjacent hypotenuse is cos. So this will be 280 cos 13 degrees. If we punch that into our calculator, we end up with 270 kilometers south. If we look at the x component, it's the opposite with respect to the angle and the hypotenuse. Opposite hypotenuse is sine. So this trig ratio, to determine the x component, would be 280 sine 13 degrees. If you punch this into your calculator, you end up with an x component of 63 kilometers in the west direction. So in this example, the y component was cos and the x component was sine. If this is cos, then this one will be sine. Knowing that will allow you to compute these x and y components quickly. So in this example, the y component wasn't cos, it was sine. But that made the x component cos. If one is sine, the other is cos. All right, now that we've broken each vector up into x and y components, our second step is to add up all the x components and add up all the y components. So I want to find delta dx total, and it's equal to 230 east plus 63 west. And we can add these up algebraically because they are collinear. But in order to do so, we have to make sure they're expressed in the same direction. So I'm going to write this as 230 kilometers east minus 63 kilometers, and I'll change that west to east. If we punch this into our calculator, the total x component vector is 167 kilometers east. And we'll do the same for the y components. We'll add them all together. We'll find delta dy total. And it's equal to 110 kilometers north plus 270 kilometers south. 110 kilometers north plus 270 kilometers south. They are collinear, but I'm going to express them in the same direction. This time I'm going to choose south as my direction. I'm going to make this negative 110 kilometers south, change the sign and change the direction, plus 270 kilometers south. If you punch this into your calculator, you end up with 160 kilometers south. So now we have our delta dx total and our delta dy total. Step 3 is to create a right angle triangle with delta dx total and delta dy total. So this right angle triangle is going to look like this. 167 kilometers east. And if you notice, I'm not drawing this accurately to scale. And our y total is 160 kilometers south. And we can find the total displacement by drawing a line that joins the tail of the first to the tip of the last. So this hypotenuse of this right angle triangle will give us the magnitude of our total displacement. And we can use Pythagorean theorem c squared equals a squared plus b squared. And just so you know, Pythagorean theorem is really the cosine law. But in the cosine law, if you were to put in 90 degrees, the cos of 90 degrees is 0. So this whole term would cancel out, and we end up with a simplified Pythagorean theorem. So the magnitude of our total displacement is equal to the square root of 167 squared plus 160 squared. If we simplify this, we end up with a magnitude of 230 kilometers. Now, in order to state the total displacement, we know the magnitude is 230 kilometers, but now we'll have to state the direction. In order to do so, we need to find the angle that this vector is pointing. So we are going to use the angle and its opposite and adjacent to find the value of the angle theta inside. Opposite adjacent forms the trigonometric ratio tan. So I know that tan theta equals opposite over adjacent, and I can find the angle by finding the inverse tan of 160 over 167. If I compute this in my calculator, I end up with 44 degrees. Now this angle is 44 degrees from the east line, and it is 44 degrees south of east. So I'm going to write this as 44 degrees south of east, and this is our total displacement. Please be sure to try the practice problems in this section of your textbook.